So, when a machine just stops and the power is out, it's not just a problem, right? It's a mystery. It's basically a crime scene full of clues, a few usual suspects, and one culprit hiding somewhere in the wires. Today, we're going to put on our detective hats and figure out how to solve it.
Okay, picture this. You're on the job, and suddenly everything goes quiet. The machine in front of you is dead. You've got your multimeter in your hand. What is your absolute first move? What are you going to check first? Just, think about it for a sec.
Now, if your first thought was something like, I'll just start swapping out parts, or I'll randomly check some connections. Whoa, hold on a second. In electrical troubleshooting, guessing is pretty much the fastest way to make a bad situation even worse. The real key here is a systematic investigation. It's all about following a logical process, not just taking a wild shot in the dark.
All right, let's dive in. Section 1, when the lights go out. It's time to take a look at our crime scene.
You've really only got two paths you can take here. One is just chaotic guesswork, and trust me, that leads absolutely nowhere fast. The other is a logical, step-by-step process that actually leads you to the solution. And for you pros out there, especially if you're taking certification exams, they're not just testing you on finding the answer. They're testing you on using the right method. The process is the answer. So here's the good news. Almost every electrical fault falls into just one of a few categories. You can think of these as our usual suspects. And if we know their characteristics, we can figure out who we're dealing with really, really quickly. Each of our suspects, they've got a unique signature, a specific way it messes with the flow of electricity. Learning these signatures is kind of like learning a criminal's MO, It tells you exactly who you should be looking for. Okay, so our first suspect, the open circuit. The easiest way to think about this one is like a broken bridge. The path for that electricity is just cut off. Could be an open switch, a broken wire, maybe a blown fuse. The bottom line is the loop's not complete, so absolutely no current can flow. Zero. Suspect number 2 is the short circuit. And yeah, this is the dangerous one. It's basically an unintended shortcut for electricity that goes around the part that's supposed to be doing the work, the load. And because this new path has almost zero resistance, current just surges to incredibly high levels. I mean, that's exactly why we have fuses and breakers, to stop this monster before it can cause a fire. And our final suspect, high resistance. Now, this one's a little sneakier. It's not a complete break, it's more like a bottleneck. Think of a nasty traffic jam on the electrical highway. Maybe it's a corroded connection or a loose wire. Current can still get through, but it's restricted. And that restriction causes components to get hot and eventually fail. So here's our case file. This is the evidence we have on each suspect. Just look at the patterns here. They're completely different. An open circuit, you get zero current, but you'll see the full supply voltage right across that break. A short, you've got almost no voltage, but a massive, massive current spike. And high resistance, that'll show you reduced current and a really weird voltage drop right at the fault. These are the exact clues we're going to be looking for with our meters. Okay, so we know our suspects, but now we need to learn how to actually read the crime scene. And that means we need to understand our circuit diagrams and know what our meter is trying to tell us. Every good detective needs a map of the crime scene, right? Well, for us, we've got two main types. Ladder logic diagrams are awesome for tracing control circuits. You just follow each rung from left to right and see where the power stops. Then you have schematics, which show you the whole system, letting you trace the entire path of the current. You've really got to master both to find where that path is broken. Okay, listen up. If you remember only one thing about using your meter today, make it this. Voltage follows the open. That means if you measure across an open switch or a blown fuse, boom, you'll read the full supply voltage. And on the flip side, voltage collapses across the short. If you measure across a short circuit, you'll read pretty much zero. This right here is the absolute key to figuring out what the clues mean. All right, we know our suspects, and we know how to read the clues. Now it's time for the real investigation, the 5-step process that every single good detective has to follow. So here it is, but before you even think about starting, let's talk safety. That is number 1. Once you're safe, then you start. 1, verify the problem actually exists. 2, gather your info. Get the diagrams out. 3, isolate the fault by carefully tracing the circuit. 4, and this is critical, with the power off, test the component you think is bad. And finally, 5, repair the problem and then verify that your fix actually worked. You follow these steps in this order every single time, no exceptions. And hey, if you're ever tempted to skip a step, Just read this quote. It says it all. The single biggest mistake people make is jumping right to testing parts without first tracing the circuit to find out where the problem even is. Tracing the circuit isn't optional. It is the investigation. All right, theory time is over. Section 5, cracking the case. Let's take our 5-step process and apply it to a real-world scenario. Okay, you're at the machine. Step 1, you check the voltage at the main power supply. It's perfect. This is our first clue. It tells us the problem isn't the building power. It's downstream, somewhere inside this specific machine. So what's the next logical place to put your meter leads? Exactly. You always trace the power from the source and move downstream. The very next thing in line is probably a fuse or a circuit breaker, so you check for voltage on both sides of it. If you've got power going in, but nothing coming out, well, you've just found the break in the path. The fuse is open. But hold on, this is where the great detectives really separate themselves from the rookies. You found an open fuse. Case closed, right? No, wrong. A blown fuse is almost never the root cause. It's a symptom. That fuse is the hero that sacrificed itself to protect the rest of the circuit. The real mystery we have to solve is what caused it to blow. So let's review the detective's handbook here. These are the non-negotiable rules. An open circuit has full voltage across it. A short circuit has 0 voltage. A blown fuse is a symptom of a deeper problem, probably a short. You always trace voltage from the source down the line, and for goodness sake, never use an ohm meter on a live circuit. These rules will keep you safe, and will lead you to the right answer. So, there you have it. You've learned about the suspects, how to read the clues, and the process for cracking the case. But the core lesson here, it isn't just about wires and fuses. It's about the power of trading pure guesswork for a systematic process. So, the question I want to leave you with is, what other complicated problems in your life could you solve by making that exact same trade?